Artificial intelligence, AI, has seen a tremendous growth in popularity. This massive increase in the number of users and large language models are driving data center owners to rethink their network infrastructure and optimize it for AI workloads. In this video, we'll dive into some of the challenges and solutions you are likely to encounter when optimizing an AI infrastructure. Also, we'll describe how to most cost and time efficiently test the performance of your solutions. AI infrastructures consist of thousands of GPUs, assembled in clusters, and connected via NICs to a high-bandwidth, low-latency switch network and the Internet. The switch architecture most often used is a spine-leaf structure. This ensures a short path with predictable latency between the GPU clusters. A lot of the AI data traffic involves large data flows exchanged between the GPU clusters and not, as is usually the case, between a client and the server. The job completion time is a very important performance parameter because it directly translates into a great user experience when interacting with an AI model. Also, in the learning phase, short job completion time means faster model updates. To support typical AI workloads in the best possible way, connections must be lossless and offer low latency. But Ethernet and IP are not designed to be lossless nor provide low latency. For this reason, it is common to use the RoCE v2 protocol for east-west AI traffic because RoCE is designed to provide low latency through direct data transfer between GPUs without CPU involvement. RoCE v2 encapsulates InfiniBand transport packets in Ethernet, IP, and UDP headers, so it can be routed over Ethernet networks. As shown here, the traffic patterns in AI networks can very easily lead to congestion, where many transmitters send to a single receiver. This causes the egress queue at the last switch to overflow. Congestion is undesirable because it requires retransmission of discarded packets, which means increased latency and, in the worst case, loss of data. To manage congestion, two mechanisms are often used together: priority flow control, or PFC, and explicit congestion notification, or ECN. PFC is the most drastic solution as it requires the senders to temporarily stop transmitting data to empty the queue of the switch. ECN is a more advanced solution, as it kicks in before the queue gets too full. ECN works by asking the senders to adjust their transmission rates to ensure the maximum amount of data is transferred without overflowing any queues in the network. Both PFC and ECN require fine-tuning of the threshold parameters for K-fill levels. And this fine-tuning is not a simple task because many different traffic patterns must be tried in a consistent manner. You could build a big test network, but that would be expensive, time-consuming, and difficult to manage. Alternatively, you could use a couple of Teledyne LaCroix Z800 Freya Ethernet traffic generators and a SierraNet M1288 protocol analyzer, as shown here. The traffic generators on the left are used to create flows with RoCE v2 and other types of traffic classes, which are then sent to the switch, which is the device under test. As the packet rate is gradually increased, the protocol analyzer and traffic generator to the right will capture, analyze, and then count the number of ECN congestion-marked packets to verify correct performance. The setup can also be used to adjust the threshold levels, Kmax and Kmin, for optimum performance. Once the PFC threshold is reached, the traffic generators on the left will also count the number of generated PFC pause frames and stop sending data. AI work tasks often involve moving huge amounts of data around, and it is therefore important to utilize the data center infrastructure efficiently. One common approach is dynamic load balancing at the flow level or even of individual packets, a technique often referred to as packet spraying. This means that the individual switches in the network dynamically determine the best path for each packet at any given time. Even though packet spraying can utilize the network very efficiently, it can also lead to some undesired impairments. For example, as individual packets in a flow between two GPU clusters can take different paths across the network, they can be received in a different order than they were sent. Misordered packets are problematic because they increase the job completion time. This can result in a request for retransmission using Go backend, or it will increase the processing time that the receiving smart NIC has to reorder the packets. When verifying performance of how the AI infrastructure handles different types of impairments, it is important to be able to generate the impairments one at a time, in a controlled manner. A good way to do this is to use an impairment emulator like the Teledyne LaCroix E100 Chimera and an infusion jammer like the Teledyne LaCroix M1288. These devices can be placed anywhere in the network, even directly between two NICs. And they can be configured to insert errors and add impairments such as varying latency, jitter, packet misordering, packet loss, link loss, packet rewrite, and much more. As you can see, at Teledyne LaCroix we have all the tools you need to test the performance of your high-speed data center network to ensure it is optimized for AI applications. If you have any questions or would like a demonstration, don't hesitate to contact us. Alternatively, visit our website and try it out yourself using our live demo system.